Hello, we are Team 21063, and we are sponsored by ASML for our project, Distortion Metrology Test for Large Field Lens. We would like to start by thanking Mirong Wang, who has been our contact at ASML, and our University of Arizona mentors, Dr. Mike Noxiger and Miriam Baker. Our team consists of Crystal Escarcega Merida, Krister Evely, John Parton, Paige Sawyers, De'Eric Smith, and Jacqueline Wyckoff, and all of us are optical engineers. In optical systems, metrology tests are often developed and utilized to characterize the type, location, and magnitude of aberrations in optical systems like lenses. If lenses are subjected to high levels of aberration, the image quality will suffer, and this can lead to errors in production. However, if the amount of aberration is known, the degrading image quality can be accounted for and potentially fixed. For our project, the goal was to research and develop a prototype metrology test which will measure the distortion and field curvature of a large field of view lens. For the testing system, distortion shall be measured to a tolerance of 50 nanometers, and field curvature shall be measured with a tolerance of 2 microns. The metrology test was designed for a system magnification of 1x. Overall, the metrology test we have developed can be implemented by ASML to accurately test the distortion and field curvature in a specific large field of view lens, which they will use in their lithography systems.
In this segment, I'll be discussing what distortion and field curvature are. Distortion describes the change in magnification across the field of view at a certain working distance. There are two main types of distortion, pincushion and barrel distortion. Barrel distortion happens because the field curvature of the lens is much wider than the size of the image sensor, so the image is squeezed, in a sense, to fit onto the sensor, causing the image to look enlarged and rounded. Pincushion distortion happens due to the image magnification increasing as it goes towards the edges of the frame. This causes the image to look as if someone is pushing on it like a pincushion. Field curvature describes how much the lens curvature causes the image plane to curve. As we see in this figure, the curvature of the lens causes the plane where the image would be to curve. As a result of this, only specific parts of the image would be in focus, while others wouldn't be.
So I'm going to be going over some of the methods behind how we made this distortion and field curvature measurement. The difficulty behind it was that we were trying to measure a nanometer scale change with only micron level equipment like micrometers and pixels that were only about 5.2 microns in size. So in order to make a nanometer scale measurement, we realized we needed to amplify the effect of distortion in some way. And how we settled on doing that was a technique called metrology. It's a really cool technique in which you can overlap two geometric patterns, in our case straight line gratings, and the superposition creates a net fringe pattern as a result of overlapping those two geometric patterns. What's really cool about it though is that a small change in one of the gratings will have a large amplified effect in the overall fringe pattern. So we decided to use this to measure nanometer scale distortion because small changes in the first grating pattern when imaged onto the second would cause an overall shift in the moire pattern, and from that we could infer distortion. Moving on to field curvature, the approach was much more simple. We decided we were just going to image one of the gratings and then use image processing software to determine the annular ring of highest contrast. Then we translated the detector in several increments on the z-axis with micrometer stage, taking an image at each increment, and then compiling the results from each of those images, we could determine field curvature.
Hello, my name is Jacqueline Wyckoff, and I will be presenting the setup and the system block diagram. Here is our setup. This setup includes a monochromatic lamp, and then the first transmission grating, which is known as our image-based grating. This grating has a reticle in the center. Then there is our lens under test, which is a 45mm relay lens. The second transmission grating, which is known as our object space grating, which has a reticle as well, but this reticle is tilted by 5 degrees. And then we have our focusing lens paired with our detector. All of our components are mounted on a micrometer to give translation along the x-axis. The first transmission grating is also mounted on a goniometer as well, so that it can be rotated about the optical axis. Our detector also has translation along the optical axis, which will be a tool used to measure field curvature. This is the design of our transmission gratings that were custom made by Photoplot. They have an active area of 15 millimeters by 15 millimeters to overfill the lens, and they have a pitch of 0.1 millimeters. If you look to the right, you will see the image space grading first, and then the object space grading to the far right, which is tilted. Since we borrowed parts from the Optical Engineering College, we did not get to pick the parts shown in our point design concept model and had to make do with what they gave us. The biggest change we had to make was how we mounted the transmission gratings to get them closer together. We ended up taping them on tip and tilt stage and used mechanical mounts to protrude them towards each other so that they could be touching. This is a close-up picture of the image space grading. One of the biggest parts of this project was the software involved to actually analyze the images we take. Our detector is connected to a computer which runs our software, which is shown in our system block diagram. Our system block diagram shows a more detailed version of our setup and shows how everything is integrated in our system, including cords, rails, mounts, and any connections.
Hi, my name is D. Eric Smith, and I will be going over the methodology behind the software we are using for our project. The software portion of our project is being used to measure the amount of distortion being induced by the lens under test. The system will produce two images. One will be a moire fringe pattern with a certain amount of distortion being imparted on the image. This image will be produced by imaging an object space grading onto an image space grading. This will be known as the distorted fringe pattern. The other image will be a moire fringe pattern containing no distortion, which is produced by physically translating the object space grading onto the image space grading. This will be known as the nominal fringe pattern. These images will be uploaded to MATLAB where the amount of distortion will be calculated. This is done by taking a segment of the fringes in X and Y for each image and plotting it versus the field position. This gives us a specified pixel value for a certain field position. Plotting the pixel intensities of each fringe pattern versus the field position will provide a pattern of the intensities for the two images. Since one image is being distorted, the intensity pattern will be shifted relative to the amount of distortion being imparted by the lens. Therefore, by comparing this intensity shift in the field position by the distorted fringe pattern to the field position of the nominal fringe pattern, we're able to accurately determine the amount of distortion being produced by the lens under test.
Hello, I'm John Parton, and I'll be summarizing the results and conclusions from this project. So one of the key aspects of this project was picking our mounts and holders such that our optical setup provided the needed degrees of freedom to allow successful alignment of the system. We can see in the picture on the left that we are controlling the tip tilt as well as the X, Y, and Z movement for our selection of optical mounting components. And this allows us to successfully align the system. So here are the results we obtained from our software we wrote. The point here is that our software can automatically calculate distortion field curvature based on images collected by the detector. The image on the left shows an intensity plot that shows how the nominal, which is an undistorted intensity curve, is shifted from the distorted intensity curve. This shift gives us the amount of distortion present in the lens. We test the lens to have 2.28 microns of distortion. The image on the right shows how the resolution of the system changes when the detector position moves along the optical rail. The slight plateau at the top of the curve gives us the curvature of the field of the system, which is about 152 microns. Now that we have established a prototype distortion field curvature test, this methodology can be adapted to test other lenses. Also, the detailed alignment and test procedure allow easy replication of this test setup. Thanks for watching.